So before we get into any more specific calculations involving the unit tangent vector and the principal unit normal vector, I want to introduce a concept mostly in a visual way, but it would be a concept you'd study in great detail in linear algebra. And it's not something that's completely new, but maybe visually it's going to be new. So the concept is called linear combinations. And let's suppose that we had the tangent vector and our normal vector. Remember, they're both unit vectors, 1 unit long each. And we know that the normal vector is perpendicular to the tangent vector if they're touching. So a linear combination means to do something like this. If we double the tangent vector and add 3 times the normal vector, so this is called a linear combination. When we wrote linear equations, 2x plus 3y equals a constant, that was a linear combination. Linear just means that these are first power, no roots, no trig or exponent or log functions, no trig functions, just some constant times tangent and some constant times normal vector. So I want to give you a quick little visual of this because it pertains to how do we know where the principal normal vector is, the main normal vector. How does it pertain? So this is the visual demonstration in this segment. So if I were to double the tangent vector, that might be about here. That's 2 times the tangent vector. And then triple the normal vector, we'll say that's about here. And we were to add those together, we could use the tip to tail method and simply put the tail of this 3n to the tip of the 2t, and then that would be the vector that starts here, and so this would be 2t and this would be 3n, and then this would be the sum of those two vectors visually. Now here is the first part of the big deal. Let's do it like the geometry teacher would say. They are all coplanar. They are on the same plane, I am now saying. So this vector here, since we're using a triangle to draw these out, this triangle represents a plane. I'm just going to call this a triangle. That triangle is on a plane. So I'm claiming that that's an important piece of information. Now, let me show you what I'm going to try to prove with this. All right. So if we have a curve, r of t, and at a point on the curve we were to have the velocity vector at that point, and that's the first derivative, correct? And I was also to draw acceleration. Let's use this here. Call that acceleration. The unit tangent vector is the velocity vector but made 1 unit long. The principal unit normal vector happens to be on the same plane as tangent and acceleration. And you could even say it's in the direction of acceleration as opposed to pointing the other side. But what we're going to be able to prove is the following statement, that acceleration is a linear combination of tangent and normal vector. That this vector I was drawing here, which happens to be a linear combination of these two vectors, that acceleration fits that description. The big deal is that means the normal vector will be on the same plane as velocity and acceleration. That's how we'll know which vector normal to the curve it is. It's not one that's perpendicular to the paper or sticking out like this or sticking even this direction. It's one that you can write as a combination of the two. Now in the next segment I'm going to prove that statement and get you, we'll call it 3/4 of the way to the sort of the key formula we're going to use, and then that's about as much as we'll have time to prove. And then afterwards I'll do a demonstration of how we can find the normal vector using this information. I didn't write it in a complete English sentence because I wanted you to imagine there's going to be some algebra here when this is done. This is going to be a formula, not just a statement in English. Alright, I'll prove this linear combination concept in the next segment.